the great force of attraction. Imagine a powerful force, hidden deep in the heart of the universe, pulling entire galaxies towards it with an invisible hand. This mysterious force is known as the Great Attractor, a gravitational anomaly that has puzzled astronomers for decades. In a universe where galaxies normally move away from each other due to cosmic expansion, this phenomenon is contradictory and pulls huge areas of space inwards. But what could cause such an immense attraction? The Great Attractor is located in the so-called zone of avoidance, a region of the sky that is obscured by the dense dust clouds of our own Milky Way. This makes direct observations difficult and adds further layers of mystery to this already puzzling anomaly. Discovered in the late 1970s, astronomers noticed that galaxies in our local supercluster, the Virgo supercluster, appeared to be accelerating towards a point in the sky. But what could cause such a massive gravitational force? According to estimates, the Great Attractor pulls galaxies into space at a speed of up to 1,400 kilometers per second over a distance of 250 million light-years. To exert such a strong gravitational pull, the mass of this hidden force must be immense, with a gravitational field far beyond what can be explained by visible matter alone. However, its exact nature remains uncertain. It's like a cosmic vortex that pulls galaxies into its depths, but we can't see exactly what's at the heart of this gravitational vortex. Could dark matter be the key? As you may know, dark matter is an elusive substance that makes up about 85% of all matter in the universe, yet it does not imitate, absorb, or reflect light, making it invisible. What we know about dark matter comes from its gravitational effects on the visible universe, and it could very well be responsible for the gravitational anomaly we call the Great Attractor. In the case of the Great Attractor, dark matter could form the backbone of this gravitational force, creating a gravitational well that bends space-time on an enormous scale. Although this is only a hypothesis, it is extremely convincing. Recent studies suggest that what we observe as the Great Attractor may be part of an even larger structure, known as the Laniakea supercluster, which contains not only the Great Attractor, but also other massive structures that guide the motions of galaxies. Here is a thought experiment to make this a little clearer. Imagine you are standing on a hill with a rock at your feet. When you kick the rock, gravity will pull you down the slope into a valley. But what if the valley was obscured by fog? You wouldn't see the valley, but you'd know for sure it was there based on the movement of the rock. This is the case with the large puller. We cannot observe it directly, but we can see the effects of its gravity, which pulls entire clusters of galaxies towards it, even though the valley remains hidden in the cosmic nebula. The Great Attractor is one of the many unsolved mysteries of the universe, one that underlines how much there is still to learn about the cosmos. As our instruments improve and our understanding of dark matter deepens, we may one day fully understand the forces that determine the motions of galaxies over billions of light years. Until then, the Great Attractor remains a silent, invisible giant that exerts its mysterious influence on the universe. Could the Great Attractor be the key to discovering even larger cosmic structures? Or does it hold a clue to the most fundamental forces of the universe, such as dark energy or the elusive nature of dark matter? Only time will tell. But one thing is certain: our journey to unravel these cosmic secrets has only just begun. Cosmic strings and the inflationary epoch. In the earliest moments of the universe, just a fraction of a second after the Big Bang, the cosmos underwent a phase of rapid, almost unimaginable expansion. This era, known as the inflationary phase, laid the foundations for the universe as we know it today. But what if remnants of this era still exist and are hidden in the fabric of space-time? This leads us to the fascinating and speculative idea of cosmic strings, hypothetical one-dimensional defects that could be the ancient relics of the birth of the universe. Imagine if the universe itself bore scars from its dramatic expansion, like cracks in ice. These would be cosmic strings. The concept of cosmic strings stems from theories of high-energy physics and cosmology, which suggest that the universe cooled rapidly after the Big Bang, possibly leaving behind these incredibly thin but infinitely long structures. Although they are extremely narrow, perhaps as thin as a proton, their mass and gravitational effects would be enormous. Cosmic strings are thought to have formed during phase transitions in the early universe, at moments when the universe cooled sufficiently for the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, to decouple from each other. These phase transitions would have left defects in the fabric of space-time itself, similar to cracks in a cooling block of ice. Theories suggest that these strings would carry enormous tension, dramatically distorting the space around them and generating gravitational waves that are detectable throughout the cosmos. Imagine you are holding a rubber band stretched between 2 points. Now imagine that this rubber band is a cosmic string that stretches across vast stretches of the universe. Although it is incredibly thin, it would have immense energy, similar to a taut bowstring. If you pluck it, the vibration would travel through space itself, possibly even creating gravitational waves that we could detect, so cosmic strings could affect the universe around them. However, despite their tantalizing theoretical potential, no direct evidence for cosmic strings has yet been found. But that doesn't mean they don't exist. Some theories suggest that cosmic strings, if they exist, could be detected indirectly, perhaps by the gravitational lensing of light or by perturbations in the cosmic background radiation. CMB. The CMB is the afterglow of the Big Bang, and its uniformity is remarkable. If cosmic strings existed, they could produce subtle, detectable distortions in this background radiation and provide clues to their existence. To understand cosmic strings, we must first turn to the inflationary phase, one of the most fascinating events in cosmological history. About a trillionth of a second after the Big Bang, the universe expanded exponentially, faster than light, growing from subatomic sizes to something much larger. This phase of inflation smoothed out the early universe, erasing irregularities that might have existed before and ensuring that the universe would be homogeneous on a large scale. Why did inflation happen? According to theories such as Alan Guth's inflation model, the universe experienced this rapid expansion due to a false vacuum state. A state in which the energy of space itself inflated the universe outwards at an incredible speed. When inflation ended, the energy was released and created the particles and radiation that eventually formed stars, galaxies, and everything we see today. But this inflation phase was not just about blowing up the universe like a balloon. It also created quantum fluctuations, tiny ripples in space-time that were stretched to cosmic scales by inflation. These fluctuations became the seeds of all structures in the universe. In fact, the galaxies, stars, and even planets we see today owe their existence to these tiny fluctuations that were frozen during inflation and later grew into the massive structures we observe. Let's take a moment to delve deeper into physics. Inflation explains why the universe looks the same in every direction. A concept known as isotropy. Without inflation, different regions of the universe would not have had enough time to interact with each other and reach equilibrium. The cosmic background radiation, which is almost uniform in temperature, is the ultimate proof of this. Inflation expanded the universe so rapidly that regions that were once close together were stretched far apart and all irregularities were smoothed out. Quantum field theory, which determines the behavior of particles on the smallest scales, plays a crucial role in understanding the inflation phase. During inflation, the universe was dominated by a scalar field, often referred to as an inflaton field. This field had a very high energy density, and when it decayed, it released enormous amounts of energy and fueled the rapid expansion. The quantum fluctuations in this field were amplified to macroscopic scales and ultimately became the seeds for the formation of galaxies, clusters, and large-scale structures that we observe billions of years later. In other words, the inflation phase was like the blueprint phase of the universe. A moment when the basic design for everything from galaxy superclusters to black holes was set in motion. But what's really fascinating is the possibility that some remnants of this phase, like cosmic strings, could still be out there, hidden in the vastness of space. One of the most promising ways to discover cosmic strings is through gravitational waves. Gravitational waves, predicted by Einstein's general theory of relativity and directly observed by LIGO in 2015, are ripples in space-time caused by massive objects accelerating. If cosmic strings exist, they could generate these waves in two main ways. By grinding and sharpening. When a cosmic string forms a loop, it can oscillate and lose energy in the form of gravitational waves. These loops, which are constantly shrinking, could be a continuous source of gravitational wave emissions. Another scenario involves peaks, sharp points on a string where the tension of the string is concentrated and leads to a burst of gravitational waves. If we were to detect such waves, this could provide indirect evidence for the existence of cosmic strings and link them to the inflationary phase. Cosmic strings could be the oldest relics of the universe, stretching across space and time, reminding us of the incredible events that shaped everything we know. Although we have not yet confirmed their existence, the search continues. And with advances in gravitational wave detection and other astronomical tools, we could one day discover these elusive structures. Are cosmic strings the hidden threads that hold the universe together? Or are they just a figment of our theoretical imagination waiting to be disproved? Either way, the story of the early universe is far from complete, and there is still so much more to discover. The heat death of the universe. If there's one thing that both fascinates and terrifies cosmologists, it's pondering the ultimate fate of the universe. Will the cosmos expand forever? Will it collapse? Or will he succumb to a slow, inevitable death? One of the most frightening theories is the so-called heat death of the universe. A future in which the universe reaches a state of maximum entropy. Without heat, without energy, and without life. It is a scenario in which everything comes to a cold, silent end, and only the faint echoes of the universe's once vibrant existence remain. The universe could end in cold darkness according to entropy. To understand the concept of heat death, we need to talk about entropy, a measure of disorder in a system. According to the second law of thermodynamics, the total entropy of a closed system can only increase over time. In the case of the universe, this means that the amount of usable energy that can do work, is gradually decreasing as stars go out, galaxies move apart, and black holes evaporate. But let's take some time to internalize this. Entropy does not only refer to disorder in the sense that we think of disorder. It is a precise thermodynamic concept. As systems evolve, they tend to transition to states of maximum entropy or maximum disorder, where energy is evenly distributed and nothing special happens. In a universe that is constantly expanding, this leads to cosmic heat death. Not because it's hot, but because the thermal energy is spread so thinly that nothing works anymore. Imagine an infinitely large room in which the air is so perfectly mixed and so cold that you could never perceive any breeze, movement, or sound. By that time, in the distant future, stars will have exhausted their nuclear fuel, galaxies will have drifted far apart, and the last black holes will have evaporated into a whisper of Hawking radiation. The universe will remain as a cold, dark space in which all matter has disintegrated into subatomic particles that drift endlessly through space. There will be no stars, no light, and no warmth. Just an eerie equilibrium in which all processes have come to a standstill and entropy has reached its maximum possible state. The universe is currently in an age of stars. For billions of years, stars have shone brightly and converted hydrogen into helium and other elements through nuclear fusion. But this process is not infinite. Stars will eventually use up their fuel. Large stars end in supernova explosions, while smaller stars like our Sun shed their outer layers and remain as white dwarfs. These remnants cool over billions or even trillions of years and fade into hypothetical black dwarfs, cold, dark, mortal remnants of stars. Even more fascinating is the fate of black holes. For a long time, it was thought that black holes exist forever, but Stephen Hawking discovered in the 1970s that they actually emit radiation, now known as Hawking radiation, and lose mass over time. Although this process is incredibly slow, it will eventually lead to the vaporization of black holes. Small black holes disappear within trillions of years, while the most massive ones could take up to 10 to the power of 100 years to completely evaporate. But in the end, even black holes are not immune to entropy. Imagine this phase. The last black hole evaporates and nothing is left behind except a thin, uniform veil of low-energy photons, neutrinos, and dark matter particles scattered across an unimaginably large and empty universe. There will be no structures, no forces that bring matter together, and no possibility of forming new stars. The universe will be a desolate sea of cold radiation and scattered particles. And it will stay that way forever. Imagine a time long after there are no more living beings, when the universe is old and lifeless, perhaps 100 trillion years from now. Galaxies have become isolated, stars have died, and black holes are slowly disappearing into nothingness. What would it look like if you could observe this era? There would be no visible light, only the faintest infrared glow from cooling remnants, such as black dwarfs, and the evaporating radiation from the last black holes. The universe would appear vast and timeless, but completely still, entropy at its peak. At this point, even the laws of nature may seem meaningless. There is no more work being done, no more energy exchanges, no more particle movements in an orderly fashion. It would be a universe in which time itself no longer has any meaning, because nothing happens anymore. You could wait an eternity, but there would be no new events or phenomena, just the quiet hum of a dead universe. Dark energy, a mysterious force responsible for the accelerated expansion of the universe, plays an important role in the story of heat death. Discovered in the late 1990s, dark energy accounts for around 70% of the total energy in the universe. It is driving the galaxies apart at increasing speed, which means that in the distant future, distant galaxies will drift beyond our observable horizon, leaving us in a dark, isolated bubble of space. If dark energy continues to accelerate the expansion of the universe, it will bring about heat death even faster. As space itself expands, the distances between the particles become infinitely large, and the universe will cool even faster. In essence, dark energy could be seen as the accelerator of the fate of the universe, ensuring that all regions of space become isolated and unreachable, and that energy is too dispersed in the universe to be of any use. The heat death of the universe is one of the darkest and most depressing predictions in cosmology. It is a vision of a future in which time marches on, but nothing of significance happens. It is not a violent end, not a cosmic catastrophe, not a fiery explosion. Instead, it is a slow fade into darkness. A final eternal silence. But as unsettling as this future may seem, it is important to remember that this process will take trillions and trillions of years, far longer than the current age of the universe. Could there be a way out of heat death? Some theories suggest that quantum fluctuations could create new universes in the distant future. Or perhaps the dark energy will behave in a way that we do not yet understand. Is the heat death of the universe really the final end? Or is there more to this cosmic story? The life cycle of the stars. Stars, the shining fiery orbs that populate our universe, are more than just twinkling lights in the night sky. They are the cosmic forges in which the elements of life are created, the engines that drive galaxies and objects that in many cases end their lives in spectacular explosions. The life cycle of a star is an incredible journey that spans billions of years and involves complex processes that transform simple hydrogen into the basic building blocks of planets, living things, and everything around us. From their birth in stellar nurseries to their death as supernovae, stars are among the most fascinating objects in the cosmos. From stellar nurseries to supernovae, the birth, life, and death of stars. Stars are formed in huge clouds of gas and dust, known as stellar nurseries or molecular clouds. These regions, which are often located in the spiral arms of galaxies, are cold, dense, and full of the raw materials needed to form stars. In these nurseries, gravitational forces lead to gas accumulations that become denser and hotter over time. When the cloud collapses, the central region begins to heat up and a protostar forms, the earliest stage in the life of a star. These protostars continue to accumulate mass from the surrounding material, and as soon as the temperature in their cores reaches around 10 million degrees Kelvin, a critical process begins. Nuclear fusion. This marks the birth of a real star, as hydrogen atoms fuse to form helium, releasing enormous amounts of energy in the process. The protostar ignites, and the pressure of the fusion balances the gravity that is trying to collapse the star, stabilizing it for most of its life. Stars lead a long, stable life. A star spends most of its time in what we call the main sequence phase. This is the longest and most stable part of a star's life cycle and lasts billions of years. Our Sun, for example, is a main sequence star that is about halfway through its 10 billion year lifespan. During this phase, the star continuously converts hydrogen in its core into helium, generating a steady stream of light and heat. What is interesting is that the position of a star in the main sequence depends on its mass. Smaller stars, such as red dwarfs, burn their fuel very slowly and can remain in the main sequence for trillions of years. Larger stars, on the other hand, burn much hotter and faster and consume their fuel in just a few million years. These more massive stars live fast and die young, often with explosive consequences. A fascinating aspect of this phase is how it affects the color and temperature of the star. Larger stars are hotter and burn in a blue or white light, while smaller, cooler stars glow red or orange. This difference in color is not just an aesthetic detail. It tells us a lot about the energy output and lifespan of the star. The red giant phase, the beginning of the end. When a star exhausts the hydrogen in its core, it can no longer maintain nuclear fusion as before. For stars like our Sun, this marks the transition to the red giant phase. The core begins to shrink under the force of gravity, while the outer layers expand outwards. As the core continues to heat up, helium fusion begins and produces heavier elements such as carbon and oxygen. In this phase, the star swells dramatically. If you put a red giant in the place of our Sun, it could swallow up the orbits of Mercury, Venus, and possibly even Earth. Despite its enormous size, the surface of a red giant is cooler than in the main sequence phase. Core, however, temperatures can rise to hundreds of millions of degrees as new nuclear reactions take place. Stars forge the elements that make up our world. The heavier elements, carbon, oxygen, nitrogen, and even iron, are forged in the cores of stars. This process is called stellar nucleosynthesis and is the reason why stars are often referred to as the factories of the universe. In stars like our Sun, lighter elements such as hydrogen and helium fuse to form heavier ones. But in the most massive stars, the fusion process goes beyond carbon and oxygen and forms elements up to iron. As soon as a star begins to fuse iron, it faces a problem. Unlike lighter elements, iron does not release any energy when it melts. This leads to a catastrophic imbalance between the inward-directed gravity and the outward-directed pressure of nuclear fusion. When the fusion process stalls, the core of the star collapses under its own gravity, leading to one of the most powerful events in the universe, a supernova. Supernova. The death of massive stars. In a supernova, the outer layers of the star are hurled into space in an explosion so bright that it can temporarily outshine entire galaxies. The core of the star either collapses into a neutron star or, in the case of the most massive stars, into a black hole. The material ejected during the supernova contains all the heavy elements that were forged in the core of the star. And this debris is spread throughout space, providing the raw material for future generations of stars and planets. In fact, everything on Earth, including the atoms in your body, was formed in the heart of a star. As Carl Sagan famously said, we are made of stardust. The oxygen you breathe, the calcium in your bones, the iron in your blood. All of this was forged in the fiery core of a star that lived and died billions of years ago. The silent end of a star. White dwarfs and black dwarfs. Not all stars end their lives in a sea of flames. Stars with masses similar to or smaller than our Sun do not explode as supernovae. Instead, after passing through the red giant phase, they shed their outer layers and form beautiful planetary nebulae. What remains is the hot core of the star, now a white dwarf. An incredibly dense object about the size of the Earth. But with the mass of the Sun, white dwarfs no longer fuse elements and simply cool down over time. In the distant future, these remains will become black dwarfs. Cold, dark spheres that no longer emit any light or warmth. These black dwarfs mark the silent end of a star's life, a stark contrast to the fiery brilliance of his earlier phases. Imagine watching the life cycle of a star as if you were watching a time-lapse video. You would see a star emerge from a swirling cloud of gas, burn steadily for billions of years, then swell into a red giant and finally shed its outer layers in a final, spectacular show. But then, as the video draws to a close, the brightness fades and all that remains is a cold, dark glow. The white dwarf who eventually cools into oblivion. This life cycle is not just a story of birth, life, and death. It is also the story of creation. Stars are the ultimate recyclers of the universe, turning hydrogen into helium, helium into carbon, and so on, until they fill space with the elements that form planets, moons, and even life itself. The atoms in your body have probably passed through several stars before they became part of you. In this sense, we are all connected to the stars. The life cycle of the stars is a testimony to the beauty and complexity of the universe. These gigantic cosmic engines create and destroy, recycling the raw materials of the cosmos to give birth to new stars, planets, and ultimately life. And although our sun will remain in its main sequence phase for billions of years, it too will one day become a red giant, then a white dwarf, and finally fade away, with the elements it has forged forming new worlds. So what happens after a star dies? Could its remnants, such as neutron stars or black holes, play an even more significant role in shaping the universe? The next chapter takes us deeper into these strange and extreme objects. Neutron stars and pulsars. When a massive star reaches the end of its life, it does not simply disappear. It can collapse into one of the most extreme objects in the universe, a neutron star. These dense remnants are so compact that a single teaspoon of neutron star material would weigh as much as 1 billion tons on Earth. But that is not the only fascinating aspect of neutron stars. Some of them rotate at incredible speed and emit radiation beams that sweep across the sky like cosmic lighthouses. These rapidly rotating neutron stars are known as pulsars and are among the most precise and extreme objects in the cosmos. Neutron stars have extremely high densities. To understand how neutron stars form, we need to take a closer look at the death of massive stars. When a star with a mass many times that of the Sun exhausts its nuclear fuel, its core collapses under the force of gravity. If the star is not massive enough to form a black hole, the collapse is stopped by a bizarre quantum mechanical effect known as neutron degeneracy pressure. At this stage, the protons and electrons in the core of the star are squeezed together to form neutrons, resulting in a dense ball of neutrons squeezed into a space no larger than a city, about 20 kilometers in diameter. Neutron stars are the densest stable objects in the universe. The gravitational forces are so intense that atoms cannot exist in their normal state. The entire mass of the Sun is squeezed into a sphere with the radius of a small city. The density is so extreme that a sugar cube made of neutron star material would weigh more than Mount Everest. Let's break down the physics. The neutron degeneracy pressure is a quantum mechanical force that arises because neutrons, like all fermions, cannot occupy the same quantum state. This creates an outward pressure that balances the inward gravity and prevents the neutron star from collapsing further. However, this equilibrium can only be maintained for stars with a mass of up to about 2 to 3 times that of the Sun. If the star is more massive, the object collapses into a black hole. Pulsars are cosmic lighthouses of high-energy radiation. Some neutron stars are more than just dense. They rotate incredibly fast, sometimes up to several hundred times per second. These rapidly rotating neutron stars are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish and the phenomenon initially puzzled astronomers. The regular pulses of radiation they observed were so precise that the team jokingly referred to the source as LGM for Little Green Man, as they assumed the signals could be of extraterrestrial origin. However, it soon became clear that pulsars are not extraterrestrial signals, but a natural phenomenon resulting from the unique properties of neutron stars. Pulsars emit beams of electromagnetic radiation, typically in the radio wave range, which emanate from their magnetic poles. When the neutron star rotates, these beams sweep across space like the light of a lighthouse. When the Earth falls into the path of the beam, we perceive a pulse of radiation each time the star rotates. But why do these rays arise in the first place? Everything is related to the extreme magnetic field of the neutron star. Astronomical stars have incredibly strong magnetic fields, which are sometimes up to 1 trillion times stronger than that of the Earth. When the star collapses into a smaller, denser object, its magnetic field concentrates, creating a powerful electromagnetic environment. Charged particles are accelerated along the magnetic field lines, and these particles emit radiation as they spiral along the field. The result is the beam of radiation that defines a pulsar. Let's imagine we are in the vicinity of a pulsar. If you were close enough to observe it, although this is impossible due to the extreme conditions, you would experience a cosmic phenomenon that is second to none. The surface of the neutron star rotates at a speed approaching a significant fraction of the speed of light, and you would feel the immense gravity of the star. In fact, the gravitational force on the surface of a neutron star is around 200 billion times stronger than that of the Earth. Even the light cannot escape the intense attraction without being significantly redshifted. Imagine seeing the beams of radiation shooting out of the magnetic poles of the neutron star as it spins. For a distant observer, the rotation of the neutron star creates a regular pulsating pattern. These pulses can be so precise that some pulsars are used as cosmic clocks, whose timing is so accurate that it rivals the best atomic clocks on Earth. Not all pulsars are the same. Some neutron stars rotate so quickly that they complete a full revolution in just a few milliseconds. These millisecond pulsars are some of the most extreme objects in the universe. It is assumed that these are older neutron stars that have been spun up by the accumulation of material from a companion star in a binary system. As the material falls onto the neutron star, it transfers angular momentum and causes the neutron star to rotate faster and faster. One of the best-known millisecond pulsars is PSR 1482446 AD, which rotates more than 700 times per second. These incredibly fast rotations generate a stable, regular pulse of radiation, which makes millisecond pulsars excellent tools for studying phenomena such as gravitational waves and testing theories of general relativity. Then there are magnetars, a type of neutron star with even more extreme magnetic fields. Magnetars are incredibly rare, but their magnetic fields are a quadrillion times stronger than that of the Earth. So strong that they can distort atomic structures and cause massive bursts of X-rays and gamma rays. In some cases, these stars experience so-called starquakes, in which the crust of the neutron star breaks up under the tension of its extreme magnetic field, and releases energy bursts that can be detected from the entire galaxy. Pulsars are not just fascinating objects in themselves. They play a key role in modern astrophysics. Because they emit such regular pulses of radiation, they are used as tools for testing fundamental physical theories, in particular Einstein's general theory of relativity. One of the most exciting applications of pulsars is the detection of gravitational waves. Gravitational waves are ripples in the fabric of space-time caused by massive objects such as black holes or neutron stars accelerating through space. When two neutron stars orbit each other in a binary system, their interaction generates gravitational waves, which we can detect by monitoring changes in the timing or pulses of a pulsar. This enables astronomers to listen for gravitational waves, even from events that take place far outside our galaxy. In 2017, a groundbreaking discovery was made when the merger of two neutron stars was observed by both gravitational waves and electromagnetic radiation. A phenomenon known as kilonova. This event not only confirmed the existence of gravitational waves, but also provided insights into the formation of heavy elements such as gold and platinum, which are created in such catastrophic collisions. Neutron stars and pulsars are among the most extreme environments in the universe. They are formed from the death of massive stars and persist as the densest known objects, with magnetic fields and rotational speeds beyond imagination. Through their pulses, they reveal the inner workings of space-time itself and help scientists test the limits of our understanding of the universe. But what happens when these neutron stars reach their limits? Could they hold the secrets of even more exotic phenomena such as black holes? Or perhaps reveal new aspects of the universe that we cannot yet imagine? In the next chapter, we venture beyond our solar system and explore strange worlds orbiting distant stars. Exoplanets and the search for life. When we look out into the vast expanses of space, we can't help but ask ourselves, are we alone? The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up the tantalizing possibility that life could exist elsewhere in the universe. These alien worlds come in an astonishing variety, some strangely similar to Earth and others completely different, with burning hot surfaces or frozen oceans. The search for exoplanets is one of the most exciting fields of modern astronomy, and with each discovery, we come one step closer to answering one of the most profound questions of mankind. Is there life out there? Discovering worlds beyond our solar system is the task of cosmologists, astrobiologists, and astrophysicists. The first confirmed discovery of an exoplanet was in 1992, when astronomers discovered two rocky planets orbiting a pulsar, a rapidly spinning neutron star. This discovery was surprising, as these planets had nothing in common with our solar system, but had extreme radiation environments and completely different conditions to Earth. Then, in 1995, a planet called 51 Pegasi b was discovered orbiting a sun-like star, marking the first confirmed discovery of an exoplanet around a main sequence star. This gas giant, around 50 light-years away from Earth, triggered a revolution in astronomy. Since then, thousands of exoplanets have been discovered with a wide range of sizes, compositions, and orbits. Some are gas giants like Jupiter, others are rocky planets like Earth. And still others are exotic worlds that consist largely of ice, water, or even molten rock. With each discovery, we learn more about the diversity of planetary systems in the universe. But why are exoplanets so important? The answer is simple: they could harbor life. If we could find a planet with conditions similar to Earth, liquid water, a stable atmosphere, and an energy source, then it is possible for life to exist there. And although no clear signs of life have been discovered so far, the search has only just begun. Some of the methods used to discover exoplanets are the transit method, the radial velocity method, and the spectroscopy method. How do we find exoplanets, especially when they are so far away and so faint compared to their home stars? Astronomers use several sophisticated techniques to discover these distant worlds. Each method has its strengths, and together they have allowed us to create a detailed catalog of exoplanets. The most successful method for discovering exoplanets is the transit method. This technique involves observing the light of a star and looking for periodic dips in brightness. When a planet passes in front of its star from our point of view, it blocks a small part of the light, causing a brief dimming. By carefully observing these dips in brightness, astronomers can determine the size, orbit, and sometimes even the atmospheric composition of the planet. NASA's Kepler Space Telescope used this method to discover over 2,000 exoplanets and revolutionized our understanding of planetary systems. Kepler's precision made it possible to discover planets as small as the Earth and even smaller. The telescope observed a fixed section of the sky over a period of years and identified exoplanets that orbited their stars every few days or every few years, depending on their distance from the star. Another powerful technique is the radial velocity method, also known as the Doppler method. This approach measures the wobble of a star caused by the gravitational attraction of an orbiting planet. When the planet pulls on the star moves slightly, which in turn changes the star's light. By measuring this tiny shift in the wavelength of light, called redshift or blue shift, astronomers can determine the mass and orbit of the planet. This method was crucial in the discovery of the first exoplanets and is particularly suitable for discovering massive planets orbiting close to their stars, so-called hot Jupiters. However, it is less effective in discovering smaller Earth-like planets that do not exert such a strong gravitational pull on their stars. In recent years, astronomers have begun to use spectroscopy to analyze the atmospheres of exoplanets. By studying the light that passes through a planet's atmosphere during a transit, scientists can identify the chemical composition of the atmosphere. This technology has enabled us to detect gases such as water vapor, methane, carbon dioxide, and oxygen. These are all important indicators of the potential habitability of a planet. The upcoming James Webb Space Telescope will take this method to the next level by allowing astronomers to search for biosignatures, chemical signs of life, in the atmospheres of distant planets. For example, the presence of large amounts of oxygen and methane in a planet's atmosphere could indicate biological processes similar to those on Earth. Imagine you are an astronomer studying a distant star system using the transit method. Every 85 days, you observe a tiny drop in brightness in the star's light, which indicates the presence of an exoplanet. As you continue to observe the light, you notice subtle changes in the spectrum that indicate that the planet's atmosphere contains water vapor and possibly even clouds. Could this be an inhabitable world? It is not quite like the Earth. It is slightly larger and orbits a cooler star, but there could be liquid water on its surface. Now you apply spectroscopy. By analyzing the light filtering through the planet's atmosphere, you discover a mixture of gases, including small traces of methane. This is fascinating because methane is often associated with biological processes. Could it have been created by life? Or is it the result of geological activity? This discovery raises more questions than it answers. But it is a tantalizing clue in the search for life outside our solar system. Let's explore the role of Kepler and the TESS mission. While the Kepler Space Telescope was groundbreaking in its discoveries, its mission ended in 2018. However, the search for exoplanets continues with NASA's Transiting Exoplanet Survey satellite TESS. TESS is designed to scan almost the entire sky, focusing on nearby stars and searching for small Earth-like planets. What makes TESS particularly exciting is its ability to find planets orbiting stars that are close enough to Earth to allow follow-up studies. This means that once TESS has identified a planet of interest, other telescopes can study it in more detail, possibly analyzing its atmosphere and looking for signs of habitability. TESS has already discovered dozens of new exoplanets, some of which lie in the so-called habitable zone, where conditions for liquid water could prevail. The discovery of exoplanets has changed our understanding of the universe. With thousands of planets confirmed and even more waiting to be confirmed, we now know that planets are common. There are probably trillions of them in our galaxy alone. Some of these worlds could be rocky, temperate, and possibly even home to life. Others might be strange and exotic, with molten surfaces or atmospheres filled with thick clouds of gas. But no matter what, every discovery brings us one step closer to answering the age-old question. Are we alone? But what does it look like in more complex systems, such as those with two suns or planets that wander through the galaxy without a home star? Next, we delve into the fascinating dynamics of binary star systems and explore the potential for life in these unusual environments. The habitability of binary star systems. In the great cosmic dance, stars often have companions. In fact, about half of all stars in the universe are part of binary star systems, in which two stars move around each other in a gravitational dance. But what happens when a planet tries to orbit two stars instead of just one? Could such a planet, caught in the gravitational pull of two suns, harbor life? Double star systems may seem like an unlikely place for habitability. But recent discoveries suggest that life could actually thrive in these dynamic and complex environments. The complex orbital dynamics and the potential for life are more fascinating than we could ever have imagined. When we think of a planet orbiting two suns, the first thing that comes to mind is the fictional world of Tatooine from Star Wars, where two suns rise and set over a desert horizon. While this scene may seem like pure fantasy, it is actually based on real astronomical phenomena. Planets orbiting binary stars are called circumbinary planets, and astronomers have found several examples of them in recent years. But how can a planet maintain a stable orbit when two stars are pulling in different directions? The answer depends on the configuration of the binary star system. In some cases, the two stars are relatively close to each other, and the planet orbits far enough away that it feels the combined gravitational attraction of the two stars as if they were a single star. In other cases, the planet could orbit one of the stars more closely, while the second star orbits further away. Both scenarios can create stable planetary orbits, but they also pose challenges in terms of habitability. Double star systems present unique orbital challenges for any planet that forms within them. Depending on the distances between the two stars and their planet, the orbits can be stable and long-lasting or chaotic and disruptive. One of the key factors is whether the planet orbits close enough to a star, known as an S-type orbit, or whether it orbits both stars at a much greater distance, known as a P-type or circumbinary orbit. In circumbinary systems, the gravitational interaction between the two stars can make the orbit of a planet more elliptical than circular. This can lead to extreme seasonal fluctuations, where the amount of sunlight a planet receives changes drastically depending on where it is in its orbit. One year could be scorching hot, while the next is bitterly cold. However, if the orbit is stable and predictable, these temperature fluctuations could still support life, especially if the planet has a dense atmosphere to regulate its climate. In systems where a planet orbits closer to a star, the second star can introduce tidal forces that affect the planet's rotation and orbit. This can lead to phenomena such as bound rotation, where one side of the planet always faces the main star, similar to how the Moon is bound to the Earth. This could lead to one side of the planet being permanently burned while the other remains shrouded in darkness. However, the region in between, known as the terminator zone, could provide a more temperate environment in which life could thrive. The search for planets in binary star systems took a great leap forward with NASA's Kepler Space Telescope. Kepler discovered several circumbinary planets, including Kepler-6, 16b, the first planet discovered orbiting two stars. This gas giant, which is around 200 light-years away from Earth, is roughly the size of Saturn and takes 229 days to orbit its two suns. While Kepler-16b is probably not habitable, its discovery confirmed that circumbinary planets exist and that planetary systems around binary stars are more common than previously thought. Kepler also discovered other circumbinary planets, some of which lie in the so-called habitable zone, the area around a star where the conditions are just right for liquid water to exist. For example, Kepler-47c, a Neptune-sized planet in a binary star system about 3,300 light-years away, orbits its two suns at a distance that brings it into the habitable zone. Although Kepler-47c is probably a gas giant and does not have the conditions for life, its position in the habitable zone suggests that smaller rocky planets in similar systems could harbor life. The habitable zone in a binary star system is more complicated than in a single star system. In a circumbinary system, the habitable zone depends on the combined luminosity of the two stars and how their gravitational forces interact with the orbit of the planets. For example, if the two stars are very different in size or heat, the habitable zone could be stretched or distorted, making it difficult for a planet to maintain stable conditions over long periods of time. In addition, binary stars often produce more solar flares and intense radiation than single stars, which could destroy a planet's atmosphere or expose it to harmful levels of radiation. However, if the planet has a strong magnetic field, like Earth, it could protect itself from this stellar activity, which would allow life to thrive in the oceans or beneath the planet's surface. Despite these challenges, simulations have shown that planets in binary star systems can have stable long-term orbits within their habitable zones. The potential for life in such systems depends largely on the specific properties of the stars and the planet's orbit, atmosphere, and magnetic field. Imagine standing on the surface of a rocky exoplanet in a circumbinary system and watching two suns rise and set. The gravitational interplay between the two stars creates a unique celestial rhythm in which the shadows on the planet change and dance as the stars move across the sky. One sun is larger and hotter and shines in a bright yellow-white glow, while the other is a smaller, cooler, red dwarf. When the seasons change, the angle of the sun also changes dramatically, causing long summers and brutal winters. This extreme variability may seem like a hostile environment, but for life adapted to these fluctuations, it could provide opportunities for evolution and biodiversity. Certain regions of the planet, perhaps near large bodies of water or in the twilight zone between the two stars, could provide stable environments where life could thrive, even if the rest of the planet experiences extreme temperature fluctuations. Could binary star systems support habitable worlds? Double star systems challenge our conventional notions of habitability, but they also expand the range of possibilities. The discovery of planets like Kepler-47c in the habitable zone of a binary star system shows that life could thrive in far more complex environments than Earth-like ones. One intriguing possibility is that life on a planet in a binary star system could be more resilient or adaptable than life on Earth. Organisms could, for example, evolve to hibernate during the planet's long, harsh winters and thrive during the short, intense summers. Alternatively, life could thrive in protected environments such as underground caves or beneath the surface of oceans, where conditions remain stable even if surface temperatures fluctuate wildly. Another exciting area of research is the study of how light from two suns could influence photosynthesis and other biological processes. Would plants on a binary star planet have to develop different strategies to obtain energy from two different types of stars? Would the fluctuating light and heat levels create new ecological niches that lead to an even greater diversity of life? Double star systems offer a fascinating and complex environment for planetary habitability. While the dynamics of these systems are more complicated than those of single-star systems, the discovery of planets in habitable zones of binary star systems has shown that life may not be limited to Earth-like environments. With future missions such as the James Webb Space Telescope, We could study the atmospheres of circumbinary planets and search for signs of life on these alien worlds. But could vagabond planets wandering through the galaxy without the heat of a sun harbor life? In the next chapter, we explore these mysterious starless worlds and what makes them so fascinating. Rogue planets. Imagine a planet drifting through the dark void of space without a sun to orbit. And without light to heat its surface. These mysterious objects, known as rogue planets, wander through the galaxy, unbound and isolated from the gravitational pull of any star. Although it may seem that such a planet would be cold, dead, and uninhabitable, recent research suggests that rogue planets could be far more complex and may even harbor life. But how are these planets formed, and what happens to them as they travel through the cosmos? How do rogue planets form, and how do they travel through space? Rogue planets are fascinating anomalies in our understanding of planetary systems. Unlike the orderly solar systems we know, rogue planets drift through space on their own, having either been ejected from their original systems or possibly even formed independently in interstellar space. There are two main theories about how rogue planets form. The first and most widely accepted theory is that these planets originally formed around stars, similar to the planets in our solar system. But during the chaotic early phases of planet formation, gravitational interactions with other planets or nearby stars can destabilize their orbits. If a planet comes too close to a massive object such as a gas giant or even a passing star, it can be completely ejected from its system and catapulted into the dark expanses between the stars. The second theory is more exotic. It suggests that rogue planets could have formed in interstellar space without ever having been part of a star system. In this scenario, dense molecular clouds that normally form stars and planets could also give birth to free floating planets when smaller clumps of gas and dust condense into planet-sized objects. These rogue planets would be loners from the start, never experiencing the warmth or light of a star. Let's imagine you're traveling aboard a spaceship to search the galaxy for rogue planets. You traverse the vast voids between the stars, where the only light comes from distant galaxies and the occasional glimmer of a nebula. Suddenly your sensors detect something unusual. A massive object drifting through the darkness. As you approach, you realize that it is a rogue planet, its surface covered in ice, while faint traces of volcanic activity indicate that there is an internal heat source. What would it be like to stand on the surface of such a world? Without a sun, the sky would be pitch black, filled only with distant starlights. The surface would be icy, possibly hundreds of degrees below freezing. But beneath the icy crust, there could be a warm, liquid ocean that is heated by the planet's internal geothermal activity. This ocean could support microbial life similar to the ecosystems we find in Earth's deep-sea hydrothermal vents, where organisms thrive without sunlight and draw their energy from the heat of the Earth's core. Could rogue planets support life? While the idea of life on a rogue planet may seem far-fetched, it is not impossible. A planet without a star would have to rely on alternative energy sources to maintain heat and stability. One possibility would be geothermal heating. Many planets, including the Earth, generate heat through the radioactive decay of elements in their cores. This heat could maintain a subterranean ocean of liquid water under a thick layer of ice, creating a stable environment in which life could develop. Such an ecosystem could resemble Earth's deep oceans, where sunlight never penetrates, and life relies on chemical energy from hydrothermal vents. These springs release heat and minerals into the surrounding water and create the conditions that simple organisms need to survive. On a rogue planet, similar hydrothermal activity could support life, even in the absence of sunlight. In addition to geothermal heating, some rogue planets may retain a thick atmosphere that traps heat through the greenhouse effect. If the planet had a dense atmosphere rich in greenhouse gases such as carbon dioxide or methane, it could maintain a relatively stable surface temperature even without the heat of a star. This atmosphere would also protect the surface of the planet from the harsh conditions of interstellar space, such as cosmic radiation. A real example of a potentially habitable environment on a rogue planet is Europa, one of Jupiter's moons. Europe has a thick layer of ice covering a global ocean of liquid water. While Europa orbits Jupiter and receives some heat from the Sun, much of its internal heat comes from tidal forces caused by its interaction with Jupiter's gravity. A similar process could occur on a rogue planet, where tidal forces or residual heat from planet formation provide the energy needed to maintain liquid water beneath the icy surface. The search for rogue planets has led us here. The discovery of rogue planets is incredibly difficult. Without a host star, these planets do not reflect light or emit heat that could be easily detected with telescopes. Nevertheless, astronomers have developed clever methods to find these wandering worlds. One of the most successful techniques is gravitational microlensing. This method takes advantage of the fact that massive objects, such as planets, bend the light from background stars as they pass in front of them. When a rogue planet passes in front of a distant star, its gravity acts like a lens, amplifying the star's light and revealing the planet's presence. The gravitational microlensing technique has already led to the discovery of several potential rogue planets. In 2011, astronomers used this technique to discover around 10 possible rogue planets, each of which had a mass similar to that of Jupiter. These discoveries suggest that rogue planets could be common in the galaxy, possibly even more numerous than stars themselves. Another potential method for detecting rogue planets is their thermal radiation. Although they have no star to heat them, rogue planets still emit a small amount of infrared radiation due to their internal heat. Advanced infrared telescopes like the James Webb Space Telescope could potentially detect these faint heat signals, especially on larger rogue planets that retain more internal energy. What happens to rogue planets over time? As rogue planets roam the galaxy, they face a lonely and uncertain fate. Without the stabilizing presence of a star, they are at the mercy of the gravitational forces of the galaxy. Some rogue planets could eventually be captured by a passing star and become part of a stable solar system again. Others could continue their lonely journeys through interstellar space, wandering for billions of years without ever coming close to another star. Over time, the internal heat of a rogue planet will slowly dissipate. If the planet has a molten core, it will cool and solidify, reducing geothermal activity. Eventually, even the thickest atmosphere will freeze, and the planet will become a frozen, lifeless world drifting through the darkness. However, for a planet with significant mass such as a gas giant, the internal heat could remain for billions of years. Even after all volcanic activity has ceased, such a planet might still retain a warm core that provides just enough energy to sustain a hidden ocean or even the faintest signs of life under a layer of ice. Imagine a future in which humanity has mastered interstellar travel. We venture into the far reaches of the galaxy and explore rogue planets drifting through the dark spaces between the stars. What secrets would we discover on these cold, isolated worlds? Perhaps we would discover frozen landscapes that resemble the icy moons in our solar system. Or perhaps we come across hidden ecosystems that thrive in the warmth of a planet's internal heat. In these distant corners of the galaxy, life could exist in forms we can barely imagine, adapted to survive without sunlight, relying on chemical energy and the faint warmth of a dying world. Rogue planets are among the most mysterious objects in the universe. Although they exist in the cold and dark voids of interstellar space, they could still hold the potential for life, especially in subterranean oceans or under thick atmospheres. As our detection methods continue to improve, we may discover that these wandering worlds are more common than we ever thought. Who knows what strange and wonderful life forms might await us on these lonely, starless planets? Could rogue planets be the key to understanding the resilience of life in extreme environments? And if we find life on a rogue planet, what would that mean for the possibility of life elsewhere in the universe? The quest to explore these distant, isolated worlds has only just begun and could lead us deeper into the unknown than ever before. Super-Earths. In the search for habitable worlds beyond our solar system, a class of planets has captured the imagination of scientists and space enthusiasts alike. Super-Earth. These planets are larger than the Earth but smaller than gas giants like Neptune. And they could be some of the most promising candidates for the discovery of life in the universe. But what exactly makes super-Earths so fascinating? And could they be suitable for life as we know it? Earth's larger cousins are super-Earths. Why are they so fascinating? Super-Earths are planets with masses between 1 and 10 times the mass of Earth. They are larger and more massive than our home planet, but significantly smaller than the gas giants in our solar system. What makes these planets particularly interesting is that they could be rocky, similar to Earth, with solid surfaces that could support oceans, atmospheres, and possibly even life. The first confirmed super-Earth 55 Cancri E was discovered in 2004. It orbits a star that is around 50 light-years away from Earth. Since then, thousands of potential super-Earths have been identified whose sizes, compositions, and orbits vary greatly. Some orbit close to their stars, which makes them hot and inhospitable. while others lie in the habitable zone, the area around a star where conditions for liquid water could prevail. One reason why super-Earths are so fascinating is that they may be more common than Earth-sized planets. In fact, observations suggest that they are among the most common types of planets in the galaxy, making them a key target in the search for extraterrestrial life. Super-Earths have a wide range of properties. Some could have dense atmospheres, while others could have rather flat, Earth-like atmospheres. Depending on their mass, these planets could also have a stronger gravity than would affect the geology to the point where life could evolve. On larger super-Earths, the increased gravitational force could lead to higher atmospheric pressures, potentially resulting in oceans hundreds of kilometers deep. Could they be suitable for life? The big question about super-Earths is whether they could support life. While we don't have a definitive answer yet, scientists are optimistic that one of the key factors in determining whether a planet is suitable for life is whether it has liquid water. Water is essential for life as we know it. And for a planet to have liquid water, it must be in the habitable zone of its star. Far enough away not to get burnt, but close enough to stay warm. One fascinating super-Earth is Kepler 452b, which orbits a Sun-like star in the habitable zone. Kepler 452b is about 60% larger than the Earth and lies in a region where liquid water could exist on its surface. Although we don't know for sure whether this planet has oceans, its size and location make it one of the most promising candidates for habitability yet discovered. Another important factor in determining the habitability of a super-Earth is its atmosphere. A dense atmosphere could help regulate the planet's temperature, keep it warm enough to retain liquid water, and protect it from harmful radiation. However, if the atmosphere is too dense, it could trap too much heat and trigger a greenhouse effect, similar to what we see on Venus. This delicate and complex balance between the precise atmospheric composition and varying surface conditions is absolutely crucial to determining whether a super-Earth planet could potentially support and sustain life. Imagine you are standing on the surface of a super-Earth and looking up into the sky. The stronger gravity would make you feel heavier, and the horizon might appear closer due to the size of the planet. If the planet had a dense atmosphere, the sky might have a different color, perhaps a deeper blue or even green, depending on the gases in the air. The planet's increased gravity would also mean that mountains and landforms would not be as high as on Earth, as the weight of the rocks would limit how high they could rise. Despite these differences, the surface of a super-Earth could feel surprisingly familiar. Oceans, mountains, and even weather phenomena such as rain and wind, all of which are shaped by the greater mass of the planet. Geological activity is also an important aspect for the habitability of super-Earths. On Earth, plate tectonics and volcanism play a crucial role in regulating the carbon cycle and stabilizing the climate. The movement of tectonic plates also leads to volcanic activity, which releases gases such as carbon dioxide into the atmosphere. Gases that help to maintain a stable temperature over long periods of time. A more massive super-Earth would likely exhibit more intense geological activity driven by its greater internal heat. This could lead to more frequent volcanic eruptions and stronger tectonic forces. While this sounds extreme, it could be beneficial for the long-term habitability of the planet. A dynamic geology would help recycle carbon dioxide and other gases between the atmosphere and the surface of the planet, potentially preventing the planet from becoming too hot or too cold. In addition, super-Earths in bound orbits, where one side of the planet always faces its star, could still be habitable. If the planet has a dense atmosphere, heat could be distributed from the sun-facing side to the night side, creating a stable, habitable zone between the two extremes. This concept, known as the Terminator Zone, could allow life to exist in a narrow strip of land or ocean between the scorching heat of the day side and the freezing cold of the night side. Super-Earths represent some of the most exciting possibilities in the search for life outside our solar system. These larger, potentially Earth-like planets could offer conditions ranging from familiar to exotic, with stronger gravity, more intense geological activity, and vast oceans. While we still have much to learn about these worlds, they are at the center of modern astronomy. And future missions could reveal whether they are really habitable or even harbor life. What if we could study the atmospheres of these super-Earths in detail, to analyze their chemical composition and look for signs of life? In the next chapter, we learn how astronomers are doing just that, using cutting-edge techniques to unlock the secrets of planetary atmospheres. Exoplanetary atmospheres. While the discovery of exoplanets, planets outside our solar system, has revolutionized our understanding of the universe, one of the most important steps in determining whether these worlds could support life is to analyze their atmospheres. By studying the chemical composition of an exoplanet's atmosphere, astronomers can learn about its climate, surface conditions, and even whether it might harbor life. The study of exoplanetary atmospheres is one of the most exciting fields of astronomy today, as state-of-the-art techniques are revealing promising clues about the nature of these distant worlds. To understand why the atmosphere of an exoplanet is so important, we should first consider what role an atmosphere plays for a planet. An atmosphere regulates the temperature of a planet, protects its surface from harmful space radiation, and provides the essential gases that life could need. On Earth, for example, our atmosphere contains oxygen for respiration, nitrogen for stabilization, and carbon dioxide for temperature regulation. If a similar combination of gases is found on an exoplanet, this could indicate that the planet is habitable or even inhabited. But how do astronomers analyze the atmospheres of planets that are light years away? One of the most successful methods is transit spectroscopy. This technique consists of observing a planet as it passes in front of its star, temporarily blocking part of the starlight. As the star's light passes through the planet's atmosphere, some wavelengths of light are absorbed by the gases in the atmosphere, while others are transmitted. By analyzing the starlight before, during, and after the transit, astronomers can determine which gases are present in the atmosphere based on the specific wavelengths of light that are absorbed. The Hubble Space Telescope and ground-based observatories have used transit spectroscopy to detect atmospheres on a variety of exoplanets, from hot gas giants to rocky super-Earths. By studying these atmospheres, astronomers can measure the temperature, pressure, and composition of exoplanets and gain insights into their potential habitability. In the future, even more detailed observations will be possible with the James Webb Space Telescope, which has been specially developed to study the atmospheres of exoplanets in greater detail than ever before. The infrared capabilities of the James Webb Telescope make it possible to detect the faint heat signatures of distant planets, providing new information about their atmospheres, surface conditions, and even the possibility of liquid water. So what exactly are astronomers looking for when they analyze the atmosphere of an exoplanet? Certain gases are considered biosignatures, which means that they could indicate the presence of life. Other gases give us clues about the climate, surface conditions, and whether the planet is a gas giant or a rocky world like Earth. Oxygen is one of the most important gases when it comes to life on Earth. It is produced by plants and microorganisms through photosynthesis and makes up about 21% of the Earth's atmosphere. While oxygen can also be produced by non-biological processes, the presence of a significant amount of oxygen in the atmosphere of an exoplanet could indicate that life exists there. Ozone, a form of oxygen that absorbs harmful ultraviolet radiation, could also indicate biological processes, as it forms naturally when oxygen interacts with sunlight. The presence of water vapor in the atmosphere of an exoplanet is a crucial indication that the planet could have liquid water on its surface, which is essential for life as we know it. Water vapor can be detected by its characteristic absorption features in the infrared spectrum. Several exoplanets, including some super-Earths and gas giants, have been found to have signs of water vapor in their atmospheres. Although most of these planets are too hot to support life. Carbon dioxide is a greenhouse gas that plays a key role in regulating the temperature of a planet. On Earth, it helps to store heat and keep the planet warm enough to support life. The presence of carbon dioxide in the atmosphere of an exoplanet could indicate that the planet has a stable climate. Methane, on the other hand, is often produced by biological processes on Earth, such as the digestion of food by animals or the decomposition of organic matter. The simultaneous presence of methane and oxygen could be a strong indicator of life, as these gases destroy each other over time in a planet's atmosphere. If both gases are present, this could mean that an ongoing process, such as Veliban, is constantly renewing them. Nitrogen is another important component of the Earth's atmosphere and makes up around 78%. Nitrogen does not react easily with other chemicals, which makes it an important stabilizing element. While nitrogen does not directly indicate life, its presence could suggest that an exoplanet has a stable, Earth-like atmosphere that could support life. Imagine you are an astronomer using the James Webb Space Telescope to analyze the atmosphere of an Earth-sized planet in the habitable zone of a distant star. As the planet passes in front of its star, you collect the data and begin to analyze the absorption lines in the planet's atmosphere. To your surprise, you detect strong signals of oxygen and water vapor. Even more fascinating are the traces of methane, possibly a biosignature. Could this be the first evidence of life beyond Earth? The next step would be to look for further signs of biological processes and observe the planet over many transits to confirm the data. The excitement of such a discovery could revolutionize our understanding of life in the universe. The ultimate goal of exploring exoplanetary atmospheres is to find biosignatures, chemical signs of life. Biosignatures could take the form of gases like oxygen and methane, but they could also include more complex molecules that we haven't looked for yet. The challenge is that many gases associated with life can also be produced by non-biological processes. For example, oxygen can be produced by the decomposition of water molecules in the atmosphere of a planet due to ultraviolet radiation. Similarly, methane can be produced by volcanic activity. This is why finding a combination of gases is so important. On Earth, the simultaneous presence of oxygen and methane is a strong indication of life, as these two gases destroy each other over time. If we were to find a similar combination on an exoplanet, this could indicate that biological processes are actively maintaining the planet's atmosphere. In addition to gases, astronomers are also looking for signs of surface features that could indicate habitability. For example, if we discover clouds or even rain on a distant planet, this could indicate that the planet has a water cycle similar to that on Earth. Observing weather phenomena such as storms or seasonal changes could also provide clues as to whether a planet is habitable. Research into exoplanetary atmospheres is still in its infancy, but it is developing rapidly. Future missions such as the James Webb Space Telescope and the European Extremely Large Telescope will allow astronomers to study exoplanets in unprecedented detail and potentially reveal the presence of life-sustaining atmospheres. These telescopes will also be able to observe smaller, Earth-like planets that were previously too difficult to study. Another exciting development is the possibility of studying exoplanets in the Alpha Centauri system, our nearest neighboring star system. Alpha Centauri's proximity to Earth makes it an ideal target for detailed atmospheric studies, and future missions could focus specifically on this system to search for habitable planets. Exoplanetary atmospheres are the key to understanding whether planets outside our solar system could support life. By analyzing the chemical composition of these atmospheres, astronomers can learn about the climate, surface conditions, and even the potential habitability of a planet. If our detection methods continue to improve, we could soon discover the first definitive signs of life on an exoplanet. A discovery that would change our understanding of the universe forever. Could the gases we detect in the atmosphere of an exoplanet indicate the presence of an extraterrestrial civilization? What other surprises could these distant atmospheres have in store for us? The exploration of exoplanetary atmospheres has only just begun, and the discoveries that lie ahead could redefine our position in the cosmos. Galactic superclusters. The universe, seemingly infinite and vast, is not randomly strewn with galaxies. Instead, galaxies are organized in a vast interconnected network known as the cosmic web. On the largest scales, this network consists of gigantic structures known as galactic superclusters, the largest known formations in the universe. These superclusters are gravitationally bound together and extend over hundreds of millions of light years. Dark matter plays a crucial role in holding these massive cosmic structures together. But how exactly are galaxies organized in these huge superclusters, and what role does dark matter play in this enormous cosmic structure? How are galaxies organized on the largest scales? At first glance, galaxies appear to be isolated islands scattered across the universe. But when astronomers mapped the positions of galaxies on large scales, a different picture emerged, one of filaments, knots, and empty spaces. This complex structure, known as the cosmic web, is a vast network of galaxies, gas, and dark matter that stretches across the cosmos. At the nodes of these filaments are clusters of galaxies, massive collections of hundreds or even thousands of galaxies that can extend through the larger structures, the superclusters, which can stretch over hundreds of millions of light years. Our own Milky Way is part of the Local Group, a collection of around 50 galaxies that also includes the Andromeda Galaxy. The Local Group, in turn, is part of the Virgo supercluster, which comprises thousands of galaxies. But the Virgo supercluster is not an isolated structure. It is part of an even larger complex known as the Laniakea supercluster. This supercluster, which was only recently identified, stretches over 500 million light years and contains more than 100,000 galaxies. The huge filaments of the cosmic web are not evenly distributed. Instead, they form dense regions of matter in which galaxies merge, separated by vast empty spaces. Vast regions of space in which only very few galaxies exist. These empty spaces can extend over tens of thousands or even hundreds of millions of light years, and are among the emptiest places in the universe. Superclusters and the gravitational role of dark matter are absolutely stunning when you imagine them in the night sky. One of the most fascinating aspects of galactic superclusters is the role of dark matter. Dark matter is the invisible substance that makes up around 85% of the matter in the universe. It neither emits nor absorbs light, making it invisible to telescopes. But their gravitational effect is enormous. Without dark matter, galaxies and superclusters could not form or hold together. In the early universe, tiny density fluctuations caused by quantum fluctuations during inflation became the seeds of galaxy formation. Dark matter, with its strong gravitational force, collected in these regions of higher density and attracted normal matter and gas. Over billions of years, these regions grew into the huge structures we see today, with dark matter acting as the glue that held galaxies and clusters together. In galactic superclusters, dark matter forms an invisible framework that influences the distribution of galaxies. Without dark matter, the gravitational force of visible matter alone would not be strong enough to hold galaxies together on such a large scale. The presence of dark matter is also evident in the way galaxies move within the superclusters. The galaxies orbit the center of mass of the supercluster, but their movements indicate that there is far more mass than we can see. This lack of mass is attributed to dark matter. Imagine traveling through a supercluster and moving from one galaxy to the next. The galaxies are not close together like in a crowded city. Instead, vast expansions of space separate them, while the force of gravity loosely holds them together in a cosmic dance. While traveling between the galaxies, you would not be able to see the dark matter, but you would feel its effect as it warps space-time and guides the movements of the galaxies like an invisible hand. In the largest empty spaces between the filaments of the cosmic web, you would experience an eerie emptiness, without stars, without galaxies, and with very little matter. But even here, dark matter is present, extending in faint, almost imperceptible strands. These filaments connect the dense knots of galaxies and superclusters and form the cosmic web that shapes the universe on the largest scales. Galactic superclusters are among the largest structures in the universe and form the cosmic web that organizes galaxies into huge interconnected networks. These superclusters are formed and held together by the gravitational effect of dark matter, which plays a central role in the formation and evolution of galaxies. As we continue to explore the cosmic web, we are discovering new insights into how the universe is structured at the largest scales, and dark matter remains one of the most important pieces of the puzzle. But what about the brightest, most energetic objects in the universe? The quasars. What role do these extraordinary beacons play in the cosmic web, and how do they influence the galaxies around them? Quasars and active galactic nuclei. In the vast darkness of space, there are objects that are so bright and powerful that they can outshine entire galaxies. These cosmic beacons are called quasars, and they are the active centers of galaxies that host supermassive black holes. Quasars are part of a larger category known as active galactic nuclei, AGN. These are regions of intense radiation and energy that surround black holes in the cores of galaxies. But how can a black hole, an object from which not even light can escape, produce such blinding brightness? The answer lies in the extreme physics that takes place just outside the event horizon, where matter spirals into the black hole, releasing enormous amounts of energy. Let's explore how these incredible objects work and what role they play in galaxy formation. Quasars are among the most luminous and energetic objects in the universe. They emit so much energy that they are visible across the entire universe despite being billions of light years away. The energy output of a quasar can be up to 1,000 times greater than that of the entire Milky Way. But all this energy is concentrated in an area no larger than our solar system. But what exactly is a quasar? At the heart of a quasar lies a supermassive black hole with a mass millions to billions of times greater than that of the Sun. When matter flows towards the black hole, a rotating disk of gas and dust forms, known as an accretion disk. The gravity of the black hole is so strong that the gas in the accretion disk heats up to millions of degrees, emitting radiation across the entire electromagnetic spectrum, from visible light to X-rays and gamma rays. The incredible brightness of quasars results from the release of energy when the gas in the accretion disk is heated by friction and gravitational forces. This energy is radiated into space and makes the quasar visible from extreme distances. The light from the most distant quasars has taken billions of years to reach us, which means that we see these objects as windows into the early universe. One of the best-known quasars, 3C273, was discovered in the early 1990s. It is located around 2 billion light-years from Earth and was one of the first quasars to be identified. His discovery revolutionized our understanding of the universe and showed that objects can exist far outside our galaxy, shining with enormous brightness and driven by processes that take place around black holes. The presence of a supermassive black hole at the center of a galaxy is nothing unusual. In fact, almost every large galaxy, including our Milky Way, has a supermassive black hole at its core. These black holes, which have millions to billions of times the mass of the Sun, exert an enormous influence on the structure and evolution of their home galaxies. When a black hole actively absorbs matter, the surrounding region becomes an active galactic nucleus, AGN. The immense gravitational force of the black hole pulls gas, dust, and stars into the accretion disk, releasing enormous amounts of energy. But the effects of a quasar or AGN do not end at the event horizon. The energy released by the accretion disk can affect the galaxy on a much larger scale. One of the most significant ways supermassive black holes form is through powerful jets of matter that are ejected from the regions near the black hole. These jets, which can extend over hundreds of thousands of light years, consist of charged particles moving at almost the speed of light. As they radiate from the black hole, these jets can inject energy into the surrounding gas and prevent it from cooling and forming new stars. This process, known as feedback, plays a crucial role in regulating star formation within galaxies. Quasars and AGNs can also heat up the intergalactic medium, the thin gas that exists between galaxies, further limiting star formation. In some cases, the energy of a quasar can even blow the gas out of the galaxy completely, stopping star formation and turning the galaxy into a red and dead system where there are only aging stars, but no new ones are born. This shows that while black holes are often seen as destructive forces, they can also play a creative role by influencing the evolution of galaxies over cosmic timescales. Imagine observing a quasar up close. From millions of light years away, the quasar appears as a dazzling point of light that outshines its entire home galaxy. If you approach the supermassive black hole at the center of the quasar, you would see the accretion disk glowing with incredible intensity and spiraling ever closer to the event horizon. Jets of charged particles shoot out from the poles of the black hole far into space, while the gravitational forces around the black hole distort space-time itself. At a safe distance, you could observe how the jets interact with gas and dust clouds in the galaxy. They form stars. The black hole's influence would extend far beyond its immediate surroundings, affecting the future of the galaxy and its ability to create new stars. Quasars are not only fascinating because of their brightness, but also because of their role in the early universe. The most distant quasars that we observe today existed at a time when the universe was only a fraction of its current age. These quasars give us an insight into the conditions of the early universe, when galaxies formed and evolved rapidly. In the first billion years after the Big Bang, galaxies grew rapidly, merged together, and formed stars at a high rate. Supermassive black holes in these young galaxies also grew rapidly, gobbling up gas and dust in the chaotic environments of galaxy mergers. The brightest quasars we see today are the result of these early black holes, which devoured huge amounts of matter and released enormous amounts of energy in the process. One of the most distant quasars, J1342 plus 029, is more than 13 billion light-years away. Its light comes from a time when the universe was less than 1 billion years old, making it one of the earliest known quasars. The discovery of such distant quasars helps astronomers to understand how supermassive black holes formed so quickly in the early universe and what role they played in shaping the galaxies around them. Quasars and active galactic nuclei are among the most powerful and mysterious objects in the universe. Powered by supermassive black holes, these cosmic beacons shine with a brightness that is visible for billions of light-years. But quasars are not just spectacular light shows. They play a crucial role in shaping the evolution of galaxies, influencing star formation and the distribution of matter in the universe. As we continue to explore quasars, we not only learn more about the extreme physics near black holes, but also gain insights into the formation of galaxies and the structure of the universe itself. What other strange and powerful phenomena might we discover if we continue to explore the most energetic regions of the universe? Could even more extreme objects exist beyond the quasars? The universe is full of surprises, and the quest to understand the forces that shape galaxies and black holes is far from over.